Alright, so with this section we begin learning what are known, I guess the best way to put it is integration technique, and contrast that with rules for differentiation. And here's what I want to say about this. We learned a lot of rules for taking derivatives. Product rule, quotient rule, power rule, sum, difference. And when you were taking the derivative of something, all you had to do was apply the right differentiation rule, and you get the derivative. It might be ugly, but there was no question about which rule to use. The idea of integration is much more creative. And we don't have rules. What we have are techniques. And it's not always immediately obvious which is the right technique to use. And a lot of times students will simply say, should I do this? Should I do that? Which one should I use? And the reality is, the only answer is a lot of practice will help you understand which rule you should use and when you should use it. And there will also be times when you're doing an integration problem and you might wind up using 2 or 3 different techniques of integration. In my opinion, integration is a lot of fun. It's like doing a puzzle. You're never quite sure what the right way is to do it, but if you're slow and steady and trust yourself, you'll get there. So as I have done a few times in the past, I've simply brought in a really powerful chart from the textbook that will help you kind of stay together with different ideas of integration. So what you see are very simple ones here. Here's the power formula backwards, all the trigonometric ones backwards, and the same thing with the exponential and logarithmic formulas. So taking integrals, finding integrals, is essentially thinking backwards when we talk about the idea of derivatives. So the way that I try to describe how to use the substitution technique for integration is you want to determine the most complicated expression and then let u, that's going to be our substitution, be the smaller part of it. And like everything else, the best way to begin to understand this is to look at a couple of examples, and so we'll go through several examples. Okay, so let's jump in with one that looks ridiculously ugly. And so this really kind of takes your breath away. But you want to try to stay calm and notice this. Here is the most complicated expression, right? Because it's a trig function, it involves e to the x, and it's being cubed. And so what we want to do, as the directions tell us, is let u equal the smaller part of this whole thing. And that probably would mean letting u equal sine of e to the x. So the next step is to differentiate with respect to x. And so du dx is equal to, well, the derivative of sine of something is cos of that something, times the derivative of the something, which in this case is e to the x. The derivative of e to the x is e to the x. And we actually want to write this as du is equal to cos of e to the x times e to the x times dx. And now what I want you to look at is this expression right here. And notice that here it is here. And so when we make our substitution, let's call this integral I, we see that now we can write I as simply u, which is sine of x, sine of e to the x, cubed, du. And the integral of that is 1/4 u to the 4th plus a constant And so what that tells us is our final result is the answer for this integral is 1/4 u sine of e to the x to the fourth plus a constant. And it's always a good idea at the beginning to check your result by taking the derivative of this thing and recognizing that you get this. So that's a tough problem to begin with, but hey, what the heck, you can take it. Okay, so here's another example, and we look and see that this is probably the most complicated expression, and so we're going to let u be the smaller part of that. We let u equal x cubed minus 5x, and we'll do two things in one here, and we'll simply write du is equal to 3x squared minus 5 dx. Look familiar? So that means when we make our substitution, that I is simply equal to the integral of the square root of u du, which is 2/3 times u to the 3/2 plus a constant, which is equal to 2/3 times u, which is x cubed minus 5x to the 3/2 plus a constant. Okay? Take a look, pause if you need to, and we'll go on to another one. Okay, so once again, this is the more complicated expression, and we'll let u be the smaller part of that. So it kind of looks like this. U is equal to tan of x. So that means du is sec squared of x dx. See it? So that means I is equal to the integral of e to the u du. That's simple, which is just equal to e to the u plus a constant. And so what we get is e to the u plus a constant. And there we go. Getting the hang of it? Alright, so for this example, what we'll do is we'll change around a little bit, and we'll look at a definite integral. And in this case, it's not necessary to make that final step of kind of going back to the x's. All we're going to do is change our limits of integration. And what's helpful to understand is these limits of integration depend upon x. So really, although we never write it, this means x is going from 0 and x is going to pi over 3. And so when we do our substitution, we're going to change those limits from being in terms of x to being in terms of u. So you'll see what we mean. Now, this is an interesting problem because you might be tempted to believe that this is the more complicated expression. And like anything else, you want to keep your wits about you. And what you want to recognize here as you look at this is that sec squared is the derivative of tan. And so really our right choice here is let u equal tan of x. And that means that du is sec squared of x dx, which we see right here. So now we're going to rewrite this integral as just u du, right? However, what are our limits? And so what we need to do is this. We have to say, well, here x was 0. Well, if x is 0, what does u equal? And hopefully you realize that u is 0. The more interesting one is up here. How about x being pi over 3? So we go back to here, and if x is pi over 3, u is the tan of pi over 3, which I believe is the square root of 3. Get it? So these are limits. Let me just try to emphasize it again. These are limits on u. And so these two integrals that we have are really equivalent integrals. One is expressed in terms of x, the other is expressed a lot more simply in terms of u. That's the advantage of the substitution technique. It usually makes things look a lot easier. So we integrate, and we get 1/2 u squared, and we go from 0 to the square root of 3, and so hopefully you realize that the solution there is just 3 over 2. Kind of cool. And I think that's it for this section. So see you next time when we look at integration by parts. Ciao, ciao.